condensed structural, you put the C and whatever follows. So this is our first, second, third carbon. So you start with your first carbon. How many things are hanging on that carbon? So just CH3. Then we've got our next carbon. How many hydrogens does that have? One. But it also has a CH3. Yes, so to show that it's a separate CH3, you put it in brackets. And then you put the third carbon. And with it, 3 H's. Yes.
If there were two carbons attached to the main thing.
You can put it 2 there. I guess that's also fine. Guys?
Now,
Yes?
do we have a condensed structural formula in our tests for next week?
I'm sure. I know there is one, and then they ask you questions about it. So, yes, know it.
How would they ask us questions about it?
They can ask you to name it, all kinds of things. Same questions that they can ask for that structure.
Or like they give it to us and then we
Okay, then explain the term structural isomer. Again, they've got the same what? An isomer, guys. The same what?
Same molecular
You have to say molecular. Same molecular formula, but different structure. Structural formula. Remember what I said when we did this in class? Whatever the name says is the thing that's different. So if it's a structural formula, they're going to have a different structure. If it's a positional isomer, then it's going to be a different position. If it's, yeah, but you're moving it. Structure counts for everything. So positional isomers, structural, and chain isomers are all structural isomers. So it's like saying students, boys, girls. Structural isomers, positional isomers, chain isomers. Okay, so now, okay, then the last one, guys, they say, what type? I'm still waiting. They're telling us butane and isobutane are structural isomers. What type, what type of structural isomers are they? So you have isobutane there. What will butane look like? 1, 2, 3, 4, just like that. So is this a positional isomer or a chain isomer? What changed position? Where?
If it's positional, isn't it with
Where was the C? Can a C be on the first carbon? Can you have one methyl? So was this even a methyl something? It's not a methyl something. And for it to have a positional isomer, it has to have the same name. This is prop. This is bute. Chain, because you had a straight chain, and now you have a branch. Yes. So if you go from a straight chain to a branched chain, it's called a chain isomer because the chain is different. Okay, then hexane is another alkane used, and they always tell you stories. Now, why I threw this one in here is that you guys must be able to see that we are allowed to mix topics. So this is asking about hexane. So as soon as you see that, you're going to think organic, right? So you can even think that C6H what?
14. Plus 2.
Double plus 2. Okay, so you know that. Then they say when hexane undergoes combustion, the energy needed to break the reactant bonds is that. And the energy released when the product form is that. So is this still an organic question?
No, it's a chemical energy question.
It's a chemical
Would that
energy.
be an activation energy?
Yes, so we can use that to calculate the delta H, the activation energy, all of that. So it says here, what is the correct, oh, you're answering the first question. The correct term for the energy needed to break the bonds, yes, is the activation energy.
This one. This one.
And we also use the abbreviation EA.
Yeah,
Okay, so activation energy,
energy and chemical change.
two, I think,
Module format.
four. Oh, yeah, two. Skip. Write a balanced equation for the combustion of hexane. Hex, you know, is C6, H14. Combustion is always plus O2. And what are the products always going to be? So we should actually say yeah for the complete combustion. Okay, so if it doesn't tell you, just assume complete. Now they say which bonds are stronger, the reactants or the products. So to break the bonds, we needed 24449. To form the new bonds, we give off 32140. So which value is bigger?
The product.
Okay, so the energy released to form the product, so it's going to be the products are the strongest. Why am I saying the products are the strongest? Because it has the biggest energy.
It's harder.
It's harder to break those bonds, yeah. I have just formed these. So if I want to break them, how much energy must I add again? That much. Then I'm going to form these and I'm going to give off this much energy if I go backwards. Which remember, we didn't really do reversible reactions, but we spoke about them a little bit.
Is this a reversible reaction? Or you just saying?
No,
Right, so it's
just
a
saying.
balanced equation for combustion reaction.
Yeah, so we're not done. There's 6 carbons there. There is only 1. What are we going to do?
Put a 6 in this.
Then there are 14 hydrogens. Remember, leave the oxygens for last. There are 14 hydrogens. There's 2. So what must I put here? 7. Now, 6 times 2. How many oxygens do I have here? 12.
Plus
Plus 7 gives me 19. So now here I need O2. So what's 19 divided by 2?
it's 9.5.
Yeah, it's 9,5. Or you can just write 19 divided by 2. Yeah, but you're not finished. Because can you have half a molecule? Yes, then you're going to times the whole thing by 2, and that 2 is going to disappear anyway. It just makes your life much easier to do it like that. So now the 2 disappears, that gets a 2, that gets a 12, and that gets a 14.
So it's
Are you with me with the method, guys? Because I do it again.
I think
You're fine. Hmm?
I'm
Okay.
so it's a 2 in front of the 19 in front of the O2 and 12 and then a 14. This is still recorded, right? Oh, is it?
I started again. Okay, then they want the delta H of the reaction. So when we have a thing like this, where they give you the values, what I would always do is just go and do a quick little graph for yourself. Because you know, it to get in there, so this, to get the energy in. So energy in, they told us, is the 24449. And then the energy out is 32140. It's more. So you're going to end up lower. So you've given, this is the energy out. Okay, now what is delta H? The difference is the delta H is actually the difference between our products and our reactants but I don't have values there, so I can just say it's the difference between my energy in and my energy out. Yes. So it's going to be energy in. Oh, yes.
I just wanted to ask what time is the ED?
Normal time, 6:30. Is that okay? It's final minus initial, right? So it's actually energy out minus energy. I think it's the other way around.
In the book it says E in minus E out.
Oh, yeah, it's right. No, 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 it is right. It won't. E in minus E out is 24449 minus 32140. Yeah, it does give you a negative, which shouldn't be the case. Are you sure this is not the other way around in the book?
Delta H equals E in minus E out.
Isn't it when it's negative? Then
Oh no, it's exo. Sorry, it is exo. It is exo. Oh, my brain was just stuck for a while. You end up with a minus something.
So it's losing energy, it's giving
So it's losing energy. So it's giving energy out. So it's exothermic. Bye-bye. What is the answer?
energy. 2449 minus 32140. 7691.
Can't be. Oh, can be.
actually, yeah, what? 7691.
What's the unit?
Kg dot mole to the one. I know what that is.
Kilojoules per mole.
Oh,
Are you sure that's right?
man, I was watching it
Six
on midterm. I was watching it. I don't know if it was an American channel, but they don't use kilojoule dot mole. They use kilojoules over mole.
Same thing.
Isn't it the same thing?
It's exactly the same.
Why do we write this way?
If you write kilojoules like that, remember when it goes to the top of the line, it becomes a -1. It's just two different ways to write it. It doesn't matter. I mix them up all the time. All right, and now for the last question, they say draw a graph of potential energy versus the course of reaction on the axis provided. Label the activated complex and delta H. Yes.
Didn't you just draw that on top?
I did. So you literally you need to make sure that the energy out is more than the energy in. Okay, so you starting here. Let's just label all of it. I've seen question papers where this is 6 marks. So here it's the energy of, what do we start with? Energy of?
I mean,
Reactants. What do we end with?
Products.
What do we call the substance here in the middle?
Activated.
Okay, no arrow. It's a substance, it's the mush, yes. So it's called the activated, yes.
I just remember that for some reason.
It doesn't need an arrow because it's a substance. But all the energies must have arrows. So they didn't ask us to label activation energy, but you know that activation energy is from the reactants to break the bonds to there. So this will be the activation energy. And then the energy between the reactants and the product there. And we want to see arrows because it's an energy. That's going to be your delta H.
So even though it's a graph, we shouldn't write any values.
Well, you don't really have values. If they say calculate the values, so I could have said I've worked this out. So I could have said equal that or equal that. If they ask you to put the values in, they didn't show. They didn't say that. They just said draw the graph. When we want values, we will tell you that we want values. Okay, last page, guys. We're doing well. We're doing so well. After this, if you can go and do this again and you're happy with it, you don't have to study anything else for the test.
When we get new sheets, so when we do them for homework, it's like a test. A little bit.
Say again?
Oh, can we get new sheets? So
Yeah, there are some leftovers here. Okay, so you want to mark yourself afterwards. Okay, then they say consider the compound fluoromethane. When you see that, are you going to get a fright?
No.
Are you going to say, oh my goodness, man did not teach us all the work?
Yes. No,
You're going to keep on reading. And you're not going to go and have a semi-heart attack because life's okay. I've taught you everything you know. Or you need to know. Not everything you know. Everything you need to know for Monday. So read the question. Is this even organic? Draw a neat Lewis diagram for CH3F. Can you do that? Yes. You're going to start with your carbon and how many electrons around the carbon? 1, 2, 3, 4. How many electrons does an H want to share? An H. One. Each hydrogen can only share one. It's in group one. It's one. Hydrogen only has one electron. It's in group one.
It can't share. It only has one electron to share once it wants to get to.
Okay, between the carbon and the hydrogen bond is 2 electrons. And they're being shared.
Oh, but be careful because hydrogen shares one of its electrons with carbon to get a full electron structure of 2.
But 2 electrons are being shared. That's what I thought you meant.
Yes, but be careful. But if you write that in an exam, we'll mark it wrong. Okay, so there's an H there, and there's an H there. Each of them, and there we have our CH3. So what's going to happen here? The F is going to share here, but now, oh, I can't use the same symbol. Please, for every element, use a different something, or highlight them, or...
Square, plus. Yes.
Okay, so there's an F. But do I get full marks? Please remember, how many electrons does F have? Which group is it in? Oh, my periodic table is not there. 7. F is in group 7. So there's going to be another 1, 2, 3, 4, 5, 6, 7. It shares one of its electrons to get a full valence electron structure. Now they want the molecular geometry. Can you see how all the topics are mixed up? 4. 4 is?
Pyramidal. Tetrahedral.
Tetrahedral.
But wouldn't it be something else because it's got 2 lone pairs at the top pushing it down?
So, that's not your central molecule. Carbon doesn't have any lone pairs. It's a central molecule. It's a central atom. Yes. Carbon will always have 4, so it'll always be tetrahedral.
Won't the top just be more negative always because
Yeah, so the fact that it's tetrahedral doesn't mean that it's symmetrical. It's different. So if it was a CH4, then it will be a C with an H and an H and an H and an H. This is still tetrahedral. So they're both tetrahedral, but are they both symmetrical? No, which one's symmetrical?
left, right?
The CH4. The CH4. But now they're asking, state whether this molecule is polar or non-polar.
It's polar.
So now you're going to say polar. Does a polar molecule got to do with electronegativity, Rory?
No,
There's also a difference in electronegativity, and there's also a difference in electronegativity. That's not what determines that it's polar. The reason why it's polar is because it's not symmetrical.
it's got negative dipoles pushing down.
Exactly. Or you can just say asymmetrical arrangement.
I was going to say there's more electrons on the top than the bottom.
That's okay. The electrons are not evenly spread around your molecule. And because it's polar, whenever you see polar, you've got 2 choices for intermolecular force? What are your two choices?
Dipole.
Dipole, dipole, or yes, dipole, dipole, or hydrogen. So which one is this?
Hydrogen. Wait.
Guys, what is our formula?
Let's think about our mistakes.
Oh no, okay,
It's dipole because of the fluorine. I think.
Guys, when is it hydrogen?
When it's NO.
NO and F with what? There is an F. There is an F. But it's not a hydrogen bond because what's not there? What's the name?
Oh, no.
Guys, the thing is called a hydrogen bond for a reason. It needs hydrogen to bond with N or O or F. If it's not hydrogen with NO or F, this is carbon with F. So it can't be a hydrogen bond. There isn't even a hydrogen there. Between the F and the H, there's no bond. So it's dipole, dipole. Please be careful. This was a tricky one because there are Fs and there are Hs. But the bond is not between H and F.